So here we are studying the second function, which is f2x x over 1 over 3. So we are studying two properties, continuity and differentiability. Now for continuity of this function implies that if the function has to be continuous at a point x, then the left hand limit and the right hand limit should be equal to the value of the function at that point. Now x to the power 1 of 3 is nice for x greater than 0 and x less than 0, so it's very easy to show that left hand limit and right hand limit will be equal to the value of the function at that point. The only condition point is x equal to 0. So let's analyze what happens at x equal to 0. The left hand limit will be equal to lim of h to 0 f2 of 0 minus h. This will be lim h going to 0 of minus h 1 over 3. This will be minus 1 to 1 over 3 and h 1 over 3. Note that this is minus 1, it's a constant, it comes out, so minus 1, limit h tending to 0, h 1 over 3, which is 0. Right hand limit will be lim of h tending to 0 f2 of h. This will be limit h going to 0 h of 1 by 3, and again this is 0. And the value of the function is 0 at that point, that is f2 0 is 0. So the function is continuous at x equal to 0 also, and we already argued that x greater than 0 and at x less than 0 the function is continuous. So we conclude that this function is continuous everywhere. Now we study the differentiability properties, and well, for x greater than 0 and x less than 0, instead of going through the cumbersome process of checking the right hand derivative and left hand derivative by using this definition f of x plus h minus f x by h, etc., etc., it can become cumbersome. So for x greater than 0, x less than 0, we can use the straightforward definition, which is basically we can use the result that d by dx of xn is nx n minus 1. So d by dx of f2x for these two regions will be equal to 1 by 3 x 1 by 3 minus 1, and this is 1 by 3 x 2 by 3. So for the function f2x to be differentiable at a point which is in x bigger than 0 and x less than 0, it is sufficient to show if this function is continuous at those points. And this function, call it say gx, is nice enough for x greater than 0 and x less than 0. Hence this function is continuous in this region. So f2x is differentiable in x bigger than 0, x less than 0. Now we have to separately handle the case x equal to 0. So here we'll use the standard definition just to be very careful. So right hand derivative is equal to limit of h tending to 0 f2 of 0 plus h minus f2 0, which by the way 0, we already proved it here, by h. So this will be f2h by h, and f2h is h of 1 by 3 by h. This is 1 over h2 by 3, and this by the way tends to infinity. Left hand derivative, limit h tending to 0. Note that here I could have just stopped and said that, hey, the right hand derivative is infinity, so it does not exist. Let's hold for a while and see what will be left-hand derivative also. So left-hand derivative will be 0 minus f to 0 minus h, f to 0 by h, and this is limit h going to 0 minus h of 1 by 3. So this is minus h minus h. This will be limit h tending to 0 of minus h. I beg your pardon, this will be 1 over minus h 2 by 3. So when we take the square inside, minus 1 square is 1, so it will be 1 over h 2 by 3, exactly like this, and this will go to infinity. So both right hand derivative and left hand derivative is infinity, which means what must be happening for this function is that at x equal to 0, the function, we already see that for negative values, this function takes negative values. So the function would be somewhere here, and for positive values, the function takes positive values. The function would be somewhere here. So at x equal to 0, both the left-hand derivative and right-hand derivative is infinity, which means the function would be becoming almost like a straight line around at x equal to 0, almost like grazing the y-axis, such that, as you see here, the tangent is a straight line. So although right-hand derivative and left-hand derivative is infinity here, we don't say that function is not differentiable, but we say that function is differentiable only the slope is infinity, which means the tangent makes an angle of 90 degree. Hence, for this function also, it is already differentiable for x greater than 0 less than 0. We can also say in the similar light, since it's also differentiable at x equal to 0, only that the tangent makes an angle of 90 degree with the x-axis. So here the tangent is, the obvious choice for the tangent here is the vertical line, but vertical lines as tangents are not allowed because the slope of such a line is 90 degree. So we will say that this function is not differentiable at x equal to 0.